All right, so we're going to start with kinetics here, which is chapter 12. So this is a little bit different than a lot of stuff we're going to talk about in this class. So this is like a entry into, I suppose, equilibrium. So this chapter does have a number of equations and formulas through it. And then, like I said, we'll get really into the heart of the class, which is equilibrium that comes after this chapter. So chapter 12, which is kinetics, deals with a couple of things. First off, there's two sort of things that we're going to talk about in this class. Thermodynamics. And thermodynamics, you probably, they teach it here at this school in 50. So in 50, you should have done some thermodynamics there in Chem 50. That was all the energy stuff. Like you did like specific heat, enthalpy, dare I say Hess's law, and adding equations together and those type of things. That's the first law of thermodynamics, which is the conservation of energy, right? Energy cannot be created nor destroyed. We will have a whole chapter after we get through a lot of the equilibrium stuff that will deal with thermodynamics. The rest of thermodynamics, like entropy, like Gibbs free energy, and those type of stuff that will kind of go with that delta H that you learned about in Chem 50. But really what thermodynamics oftentimes looks at is the idea of whether or not a reaction is spontaneous. And it's a good time to talk about it. And we'll talk about it when we do get to that thermodynamics chapter. Sometimes people have a misunderstanding about the idea of a reaction as spontaneous. So sometimes people think they hear the word spontaneous, they snap their fingers and the thing's going to happen like really fast. And that's really not what spontaneous means in the sense of chemistry and reactions. What spontaneous means is essentially what it says there for thermodynamics. It means under those conditions, would we expect this reaction to take place? And that reaction, if it did take place and is spontaneous, you could have lots of spontaneous reactions that are like super fast. And you can have a lot of spontaneous reactions that you sit there all day for it to happen, but it will eventually happen. So when we think about thermodynamics and we think about reactions being spontaneous, it has really nothing to do with how fast or slow the reaction takes place. That is what we're going to deal with in this chapter, which is kinetics. And kinetics deals with how fast or slow, for example, a reaction takes place. So again, sometimes when we get into that sort of spontaneity, people always think, okay, it's happening really, really fast. But again, we're going to deal with sort of how fast a reaction takes place here in this chapter. So if we have a reaction such as this, where we have A goes to B, and A is obviously our reactants, as we talked about the other day, and B are our products, right? When this reaction takes place, would I expect in this situation the concentration of A to be increasing or decreasing with time? What do we think? Should be decreasing, right? The reaction is heading towards the product side. And that means as this reaction takes place, the only way to get to our products, right, is to use up our reactants. And we would expect the concentration of A to start to come down, just like we would expect in this particular case, the concentration of B to start to increase with time, right? So as time goes on, we should be making more products and we would see that sort of increase in the concentration of B. By the way, when we talk about a reaction rate, a lot of times what we're dealing with is the change in the concentration of a reactant or product with time. That's a rate, right? A rate is how fast you're doing something over a period of time, like when you're driving, right? That's your rate. You're going like, of course, 40 miles an hour, obeying the speed limit and all that good stuff. That basically is how far you're going in an hour, right? You're going, if you keep that rate all the way through, you're going 40 miles in 1 hour, basically is how far you're going to travel. So in reactions, we look at really the change in concentration over time. And that is what the units there are: molarity over seconds. And when we see, by the way, a bracket like this, this does mean concentration. And usually, again, our concentration unit is typically molarity, which is moles per liter, right? So that is typically the units of concentration that we deal with. So for a reaction like this, we could actually write what is sometimes referred to as a rate expression. And we could say that the rate is equal to negative the change in the concentration of A over the change in time. Now, as we just talked about, we would expect that the concentration of A be decreasing with time. And that is why for our reactant there, we actually have a negative in front of it. I'm going to explain to you why that negative is there really in just a second. Now, when we go to B, we could write another rate expression for B, which is the change in the concentration of B. And that's what the little triangle or delta symbol means, change. The change in the concentration of B over the change in time. And there is no negative there on our product side. And that is because we would expect, as we just talked about, the amount of B should be increasing with time. So when we take a change of something, right, usually when we do some type of change, like the change in the concentration of A, that is usually the final concentration of A minus the initial concentration of A, right? That's usually how you take a change of something, kind of final minus initial. So if we just think about this logically here, but one important thing before we think logically, I think we should still be thinking logically, but we also want to know that, for example, the rate here should technically always be like a positive number. So that rate that you get for a reaction is typically a positive number. And this is why our negatives are where they are in these expressions, because if we take a look at this reaction and we just, for example, make up some concentrations. So let's just say initially we had 4 molar of this guy and nothing of this guy. And let's just say at the end there, we had 2 molar of this guy, and we'll just call it 3 molar of this guy. So when we would go to calculate the change in the concentration of A in my made up example here, we would take the final concentration, which is 2, minus the initial concentration, which is 4, and that's going to give me what type of number? A negative 2. And that negative, which would be here, along with this negative, will turn my rate into a positive number. And that is why we have that negative in the front of it for our reactants. Now, if we look at our products, we don't really need the negative there because it's increasing with time. So if I did the change in the concentration of B in this case, it would be 3 molar minus 0 molar, and that gives me a positive, right? B, which goes with my positive that's not there or is there, and that gives me again back to a positive of a rate. So we do incorporate that negative into the rate expression for reactants, because when we do the calculation of the change in the concentration of our reactants, we will end up with a negative number, and that negative basically will then turn our rate back into a positive number, which is what we do need. Any questions on that there? All right. Now, we can look at kinetics a lot of different ways. And I will say this chapter is very heavy on graphs. We like graphs in this chapter, as you will see as you go through some of the problems. Sometimes the only way to solve some problems is to like open up Excel, make a graph, and use the information there. So kinetics has a lot of graphing type of information, and we will see a number of graphs as we kind of go through these sort of calculations. But here we can see if our A is sort of the black circles and our B is the red circles, we can see that initially it's pretty much all reactants. And as time goes on, we start to see some appearance of our red and also our disappearance of our black circles, which means, again, our reactants are coming down, our products there are coming up. We also see that graphically here at pretty much time 0, we have no products. It is all reactants. And again, we start to see a decrease in our reactants followed with that increase there, obviously, in our products that are being made. And at the end of the reaction, mainly products, as these are pretty much one-way street type reactions. Nobody's coming back the other way. It's all going to kind of dump off or into the product side for the most part. So how can we kind of follow the change in concentration in a laboratory type situation? You will do this in the first real experiment. You'll do it in the second part of the first fake experiment next week. No, I'm just kidding. But you'll do something very similar to this. So for example, if we look at this reaction, which is Br2 plus a little, I'm going to go with formic acid on that. And we're going to get some bromide, a little H plus, and a little CO2. So really the Br2 here is this color. And these guys on this side is colorless. Yeah. And we could follow the absorbance values of this solution over a period of time, and that will help us. And in case you're not familiar, you can use something like a spectrophotometer, and basically it has a light source, right, at a specific wavelength that you shoot through your sample, and it goes to a detector, and it usually measures one of two things. It usually measures the absorbance, which is how much light gets absorbed by your sample, or it might sometimes measure percent transmittance, which is sort of the ratio of light that went into the light that reached the detector, basically. Now, absorbance is usually what we look at, and there is something known as our friend Beer's law. That's Beer's law. That is absorbance. That is concentration. That is what is sometimes referred to as Beer's constant. There's also a different version, A is equal to EBC. The E there's the epsilon, basically, and B, the E and B is basically the path length and the molar assortivity. A lot of times those are sometimes bundled together into Beer's constant part of the equation. The A, big A there is still absorbance, and C is concentration. Here at this school, we usually roll with more so this equation for Beer's law and stuff like that. So absorbance, right, is based on color. The darker the solution, do I have lower or higher absorbance? It is higher, right? So the darker the solution, more light's going to get absorbed by the solution. Less of it's going to reach the detector, right? And obviously, as the solution gets lighter and lighter, we will have less and less absorbance, right? So as we're rolling through here with time through these beakers, we should have our most absorbance right over here, right? And as we get towards that last one, that's not very much absorbance what's going to happen. So you can graph something, for example, like absorbance versus time. And what you would see is, you know, sort of a decrease. And what you would probably see is a decrease. And eventually, right, when we get to that beaker on the right there, of a death of your absorbance, right? Because you have no more color. It'll sort of bottom out. And by using basically the part where it's decreasing, we can relate it to basically the concentration of those guys by using something like Beer's law. We could figure out Beer's constant. You'll have the absorbance at every second, 2 seconds, however many seconds you took readings, and you could turn those basically absorbance values into concentration. So the amount of absorbance is proportional to the change in the concentration here of the Br2, as the Br2, right, is the only thing with color. So we know as the beaker loses color, we are definitely making products, as everything on the product side is colorless, and we know this reaction is proceeding. By the way, we usually set the wavelength to what is referred to as the maximum absorbance wavelength. And what you typically do is you take your sample, maybe the darkest sample, and you measure it at different wavelengths, like down here. And you'll get a graph something like this. And we typically want to grab the wavelength at sort of the peak. Why would we not want to grab the wavelength like over here? Because in terms of absorbance values, right? That's pretty much all you got available to you, which is not a lot. Yeah. You don't want that spider to bite me? Is it? Okay. I don't, but thank you. It's on the wall? All right. Well, if I go down, find a biologist or something that help me as well. No, I'll be okay. Thank you, though. So in this case, if we did set the wavelength over there to sort of the ends, we will have a lot of our samples right off of the scale. You'll get a lot of errors because you don't have enough absorbance. So that's compared to here where we have kind of maximum absorbance. We could take absorbance readings all the way up to the top of that peak, and that's going to allow us to really get our samples. So one of the things we will also do in these experiments, including next week when we do the second part of it, is it like right behind me gonna eat me? Is it? Wow. I'm like, really? Oh, that guy right there? Oh, he's just kind of hanging out. I'll be okay. Oh, there. I'll be okay. Oh, no, I'm good. It's okay. Thank you, though. I'll leave him in peace. We won't hurt him unless he starts moving. No, I'm just kidding. All right. So so we will set our wavelength to that so that we can get really all of our samples to be on scale. Now, when you do this, you will have basically this graph a lot of times when you do the experiments, and it will ask you, it will also select it for you, but you also want to kind of move it to the right absorbance value. By the way, when I set the wavelength, for example, for this solution here, which is kind of a orangey reddish color, would the wavelength of light reflect the red wavelength? It does. So the color that we see, right, is complementary to the wavelength of light that is being absorbed, right? So we wouldn't set it to the range of like orange or red, which is a much longer wavelength, right? If you remember the visible part of the spectrum, we would set it more so to as complementary colors wavelength, which is why you see in this particular case, it's like 393 set, which is not the wavelength for red. Again, it's the wavelength more for its complementary color. Any questions on that there? All right. Yeah, it'll be somewhere in that area. Yeah. All right. So the as I scribbled on the bottom there, the change in the concentration of BR2 in this particular case is again proportional to the absorbance. That's what the little symbol in the middle of those two mean, is proportional to. Would spectrophotometry be really good if all I have are colorless solutions? No, because all you're going to get is zero absorbance for everything. So you won't be able to follow what's happening in that reaction. So although this is a very good sort of way to follow the change in concentration over time, you do need some type of color to be able to do that. Either you need some reactants that have a color, right? Or even you could start with colorless, and then if it makes something that is colored in terms of a solution at the end, then you'll be able to kind of measure the color starting to come in. And your graph would be opposite. You would have like on low absorbance first, and then you would start to see a rise in absorbance on the back end of it. So if we did a graph such as this for the time of this reaction versus the concentration of BR2, we get this graph here. And there's two types of rates that we talk about. One is an average rate, and one's an instantaneous rate. And I think of average rates as sort of what's happening over the overall sort of reaction from kind of beginning to end. Instantaneous rate is sort of just for a specific period of time. So if we go back to, say, driving, so let's just say this weekend you're driving out to spring training in Arizona. I am, by the way. I'll be leaving tomorrow. So let's say on my drive, of course, I'll be obeying the speed limit the entire way. But let's just say, hypothetically speaking, I'm doing 70-ish. It's okay when you get out to Palm Springs, you can do 70. Then you get across the border, you can do about 75, I think, when you get across the border. So that ain't bad. But let's just say along the way, I averaged maybe 70 miles per hour on my trip, right? But throughout my entire trip from here to there, there might have been hypothetically pockets of a time when maybe I'm driving 75, 80, 25 like a responsible driver, right? You get hit on the freeway, 40 or so forth. So there will be pockets of time, right, that maybe you're traveling faster, right? And there will be pockets of time where you're maybe traveling slower. But if you sort of average out the entire trip from beginning to end, maybe you did drive at like 70 miles per hour. But again, there could be windows that maybe you're driving 80, 85 miles per hour. Hopefully, no cops are behind you at that window of time when that is happening. Um, and for that instantaneous moment of your trip, you're traveling faster, right? And maybe earlier you're traveling slower and stuff like that. But on the average, you are traveling at a certain sort of miles per hour. And that's what we typically look at. So in that earlier sort of rate expression, for example, that rate expression where it says rate, that is typically the average rate of the overall reaction. And this is how reactants happen. At some points, it's happening faster. Some points, it's happening slower. You know, as you get to the end, right, of a reaction, there's probably not a lot of things reacting very fastly, right? So it's going to maybe slow down and stuff like that. At the very beginning, maybe it's going to react really quick because there's lots of reactants present. They're going to be able to start reacting with each other really, really fast. So that's more of an instantaneous rate versus an average rate. And again, the average rate, for example, in this case, we would take the final concentration of Br2 minus the initial concentration of Br2. And again, our change in our time. You can, for a window of time, take the slope of the tangent of those lines, picking out a couple of points, doing a little math there if you like to. We're not going to probably do too much of that in any type of calculation, but if you take kind of the slope of that tangent of that line, you can sort of figure out your instantaneous rate for that kind of period. So, like I said before, we like a lot of graphs here in kinetics, and here is another way that we can display sort of the information for this particular reaction. Now, when we look at just the rates at specific periods of time in this particular reaction, they are not constant, but there is a relationship where they do become constant. And that is what we see here on this last column. And when we look at this, which is written like this, and we're going to talk about it a little bit later on in this chapter, this is what is sometimes referred to as a rate law. And this rate law is the rate of the reaction. K here is, let's draw it like that, little k, lowercase k. The reason I draw it like that or write it like that is big K is equilibrium constant, which is pretty much what this class is brought to you by, the big capital K. So if you write capital K, people think you're talking about equilibrium constant. Small lowercase k is what we talk about here, which is known as the rate constant. So the rate constant kind of tells you how fast this reaction is basically kind of taking place. And this is obviously the concentration of our reactant. Now, if we rearrange this equation and solve for the rate constant, what you see here is we do hit a constant value for this particular reaction based on the reactants and based on the temperature that's occurring here. So a rate constant, you could kind of think of it as sort of how fast or slow the reaction is taking place. Large rate constant might be happening really fast. Smaller one might not be happening as fast as well. And we do get actually a linear relationship here when we look at the rate versus our concentration. And in this case, if I took the slope of this line, right? Slope is rise over run, right? Rise in this case is the y, which would be rate. Run would be x, which is the concentration of Br2. That looks very much like what we have here. That's typically in these type of graphs how you can sort of graphically figure out the rate constant for a particular reaction. You get this linear sort of relationship, and sometimes you can take the slope of it and it will sort of give you that sort of rate constant. Now, what happens if we do not have any type of solution that maybe has a color? So as we talked about before, sort of using absorbance is not going to be very helpful here. So in this particular case, everything here is colorless. Disregard the yellow they put in there so you can actually see it in the picture. But other than that, pretty much everything else here is colorless. So in this particular case, we are generating a gas, right? And what we could do in this particular case is use our friend, the ideal gas law, right? That is a little PV equals nRT action. By the way, the pressure, if you use the ideal gas law, it needs to be in what units? ATM, right? Volume should be in, yeah. N should be moles, yeah. T should be, it's getting quieter here, Kelvin there. R is our gas constant, right? That's at 0.08206 liters atmosphere Kelvin mole, or 0.0821. People like to use these days for that number. So because we have obviously no solution or anything here that has any type of color, again, as I mentioned, kind of measuring the absorbance values is not going to be very helpful here. But we do have a pressure. So you maybe think to yourself, well, I can monitor the pressure for sure, right? So I can monitor the pressure in this case, but how is that going to help me? If we take the ideal gas law and we solve it for N divided by V, that would give me P over RT. Once again, N is moles, right? V is liters, and moles over liters is the molarity. So in this particular case, by following the pressure change, the temperature is probably going to be constant. R is a constant. So by following really the change in pressure in this case, we could use something like the ideal gas law and relate it to how the concentration of our gas here is changing over time by simply just following the pressure, in this case, over a period of time. By the way, the only way that we would get pressure in this case is this reaction when it has to be taking place, right? Because on the reactant side, are there any gases? There are no gases on the reactant side, which means the only way we're going to get any pressure is we got to produce that oxygen, which is on the product side. And as we start to see the pressure start to go up, then we know we're definitely making some oxygen gas. And this reaction is definitely happening, right? Going towards the product side, we're starting to see an increase in the amount of pressure that's there, which is only in this case going to be based off of oxygen being there. So otherwise we would have no gas that would cause any type of pressure. So as you can see here, simply really by just following the change in pressure and the change in time, you basically can relate that to how the concentration of O2 is changing with time. So again, you could do kinetics experiments, even perhaps if you don't have anything that has a color that you can follow the absorbance. If you have something with gas, you could just follow the change in pressure over time. And again, you could relate it sort of to kinetics material. Any questions on that there? Yeah. All right. So let's talk a little bit about an important thing, which is everybody's favorite thing, which is stoichiometry, right? So obviously we do have to take into account when we look at equations, right? We have to take into account what's going on, because things don't always react in sort of a one-to-one relationship in terms of their stoichiometry. Stoichiometry, right, as we talked about the other day, coefficients, right? Mole-to-mole relationship that's happening. So if we look at this particular reaction, we see here that for every 2 moles of A that react, we're going to produce basically 1 mole of B. So what that does to our rate expression is, if we want to sort of combo everything together, which you might want to do, to take into account both the stoichiometry and the kinetics aspect of what's going on, we could take, for example, for our reactant here, the rate would equal negative, because it is a reactant, 1 over the coefficient. So that's where the 2 comes from. So it's 1 over the coefficient. What that's going to do when you take 1 over the coefficient is going to really combo the stoichiometry part of the calculation with the kinetic part of the calculation. So you don't have to kind of do them separately. And the rest of it is very similar to what we saw earlier. the change in the concentration of A over the change in time. When we get to our product side, it will be positive. The coefficient here is 1, so that's essentially 1 over 1, which is equal to 1, which is why there's nothing written here, because you don't really need it because it's 1. The change in the concentration of B over the change in time. So in general, when you have a reaction, you could write a rate expression like this, where you basically, for our reactants here, we have our negatives, and we take, again, 1 over the coefficients. For our products, because it should be increasing with time, we don't have the negative, but we still do 1 over the coefficient. So I will say that you can do it like this, which is probably a good way to do it, to kind of put both of those things together. You could also, and maybe we'll take a look at it in one of the examples we do, you could also kind of just do a stoichiometry problem first, kind of a mole-to-mole relationship type problem, and then kind of roll into the kinetics part of the calculation. So you can separate it if you would rather do it that way. But this kind of does it all together, bundles it together, super bundling here of everything together, and it will kind of do it all in one step. But again, you can kind of do the stoichiometry part first and then roll into the kinetics part of it. Why is this important? Well, the rate here is our average rate, which should be a positive number. And what this allows you to sort of figure out is, as long as you know one piece of information about this reaction, maybe you know how C is changing with time, you can then use that information to figure out how D is changing with time. You can use that information to figure out how B or A is changing with time. You could also use that information to figure out the average rate of the reaction. Or if you even know the average rate of the reaction, you could use that to figure out how everybody is changing with time. So since everybody is equal to each other, you could write the entire thing out like this for everybody in the equation. You also, for example, if you were maybe had information about A and you were just interested in D, you could just pull out those guys' sort of rate expression and use them separately. So you could say the rate is equal to minus 1 over A, the change in the concentration of A over the change in time. The rate is equal to 1 over D, change in the concentration of D over the change in time. So let's just say we did have this information and we were able to get this number right here. How would that help me with trying to figure out this guy? Are these two numbers related to each other? Are they the same or different? They're actually the same number. Yeah. So this number here is that number there. They are all part of the same rate, right? Same reaction, which means they all will have the same average rate, right? Although they may be changing, as we talked about, differently over time, but the average rate for that reaction that they're in will be the same number. So this is how we can kind of relate one thing to the other. We could figure out, for example, again, if I knew about A over how A is changing, I can figure out the average rate for the reaction. I then can use that average rate for the reaction to figure out how D is changing with time when you do the calculation. So any questions on that part of it? Yeah. So why don't you write the rate expression for this reaction and see what you come up with here. Okay, let's take a look here. So the rate is going to equal, this is CH4, coefficient is 1, so we're going to go negative because it's a reactant. We really don't need to do the 1 over 1 because it's just going to equal 1. The change in the concentration of CH4 over the change in time. That will equal our next reactant, which will also be negative, but we do have a coefficient, so 1 over 2 for the coefficient, change in the concentration of O2 over the change in time. Now we're heading to our product side where we would expect it to start to increase. Again, the coefficient here is 1, so we don't need to do 1 over 1. We also, again, do not need the negative there on the product side because it should be increasing with time. That will give us a change in the concentration of CO2 over the change in time. And that will give us 1 over 2 for our next guy, which has a coefficient of 2. Change in the concentration of H2O over the change in time. Any questions on that one? Yeah. Yeah, the instantaneous rate you would You would really more so probably has to do some graphing and probably do that kind of slope of the tangent and stuff like that in the sense. This is again going to be more so your average rate that we're looking at in this situation. Other questions? All right, so let's try one with some actual numbers here and see. Let's say for a reaction given, the I minus changes from 1 to 0.868 molar in 10 seconds. Calculate the average rate for the first 10 seconds and the change in the concentration of H plus over the change in time. Okay, let's take a look at this. So we got some information given to us, which is we have the initial concentration here of I minus, which is 1 molar. We got the final concentration of I minus, which is 0.868 molar. And we have really our time here, which is 10 seconds. So you could kind of initially probably 0, right? And final time 10 seconds, right? In this case. So in this case, we're looking for H plus. We're given information about I minus. So the first thing we might want to start with is the rate expression for each of these. So the rate expression for our I minus that was given to us would be -1/3 because of the coefficient and it's a reactant. The change in the concentration of I minus over the change in time. We also can write the rate expression for H2, which we're interested in as well, or H plus, I'm sorry. And that would be the rate is equal to -1/2, the change in the concentration of H plus over the change in time in this case, right? So obviously we do have the information for I minus, so we could put our information into that rate expression. And if we do that for I minus coming this way, our rate would equal -1/3. Remember that we do want to do final concentration minus initial concentration. So that would be 0.868 minus 1 molar divided by, again, 10 minus 0 seconds. The reason, again, we want to do this is that's going to give me what type of number? It's going to give me a negative number, right? And again, with this negative, we'll turn our rate into a positive one, which is what we're looking for in this particular case. That means that we have 0.868 minus 1 divided by 10 and divided by 3. Once again, dividing by the 3 is taking into account the stoichiometry, basically, of this reaction. And what do we got there? We end up with a rate here that is equal to 0.0044 units are molarity on top, right, per second. That is technically the average rate of this reaction, right, that's happening in this case. Now, that's going to be helpful because if we now look at H plus, which is what we're interested in, we have the rate is equal to minus, bless you, 1/2, the change in concentration of H plus over the change in time. And in this particular case, that is pretty much what we're looking to solve for. So we do have this guy at 0.0044 molar seconds equals -1/2, change in concentration of H plus over the change in time. I need to multiply 2 to the other side. Yeah. In addition to the 2, what else should I multiply to the other side? The negative, right? So negative's got to go over to the other side. So we'll do that. And that's going to give me a negative 0.0088 molar seconds is how the H plus is changing over time. Why is that answer negative? Does that make sense? It does, because H plus is a reactant, which means it should be negatively changing over time, right? You're actually losing that much concentration over time. And that's why we do end up with a negative here, because we're looking at really the rate at which it's really the rate of disappearance, right, of our H plus in this particular case. By the way, the H plus is actually changing at the same rate as the average rate or different? Yeah, it's actually changing twice as much, right, as the average rate. And that makes sense because the coefficient, right, in front of H plus is 2, right? So that is the relationship of the stoichiometry part of it, right? Because there's 2 moles of it, it is actually decreasing at twice the rate as the average rate of the entire reaction that's happening in this particular case. Question on that one there. Okay, then let's try another one here. You have this reaction here. You start with 2.4 times 10 to the 2 grams of NOBr. Has a molar mass of 109.91 grams per mole. Throw the mole in there. Decomposes in a 2 times 10 to the 2 flask at 5 minutes. What is the average rate of Br2 production? So see what you come up with. We basically want to know how is the Br2 changing with time. Yeah, so let's take a look, see how you're doing. So here we're given some information about NOBr. We eventually want to get over to Br2. So we do want to perhaps just think about the rate expressions for each of those guys. So if we did it for our NOBr, it would be the rates equal to negative because it's a reactant, 1 over the coefficient there, the change in the concentration of NOBr over the change in time. For our Br2, we would have a rate law of our rate expression of the rate is equal to would be positive and the coefficient is 1. So it would really just be the change in the concentration of Br2 over the change in time, right? Obviously, at this point, we do have grams of NOBr. We do have the molar mass and we do have the volume it's in. Which means that we can really figure out the molarity, right? So that is one of the things we probably should do. So we'll take a little 2.4 times 10 to the minus 2 grams of NOBr. We'll use the molar mass that was given to us. Otherwise, if it was not, you would go to the periodic table to find that. And that's going to give us here, in terms of grams, 2.4 divided by 109.91. And we'll go 2.1836 moles. We then can divide it by our volume, which is basically 200 milliliters, which obviously we do need to convert into liters. Divided by 1,000 will give us 0.2 liters. And that's going to get us here, we'll call it 10.918 molar. Any questions on that so far? All right. We also are looking for ultimately the time aspect of it in seconds, and we do have time in minutes. So maybe it'll just make sense to convert our time into seconds at this point, so everything's in the right unit. So we'll do that there. I think there's still 60 seconds, I hope, in a minute. That's going to give us 300 seconds, right? So at this point, we can go into our rate expression for our NOBr because we now have pretty much all the information. So for our NOBr, it would be the rate is equal to minus 1 over 2, negative 10.918 molar divided by 300 seconds. Why did I negative that guy out? It is a reactant, which means technically the way we would get that number, right, would be take final minus initial, which should lead us to a negative number because it is a reactant decreasing with time. We just happen to have sort of the end result of the kind of beginning and end there. And obviously the 300 there would be kind of like 300 minus 0 in a sense. That also will again turn our rate into a positive number, which it does need to be. So if we do all that here, a little dividing by 300, dividing by 2, that would be good. Going to give us 0.0182, I'll call it, maybe on around, molarity over seconds as our average rate. Yeah. It would be, so this is decomposition reaction. So we assume that it's all going to basically going to go away in this case. Yeah. Other questions? So we got that, which now we can turn to our rate expression for our Br2, which is the change in the concentration of Br2 over the change in time. And that equals the rate, which is this number right here, which means that would be our number. Yeah. Not much to calculate there, right? And that is also a positive number, which also makes sense as the Br2 should be increasing with time. And it is basically changing, bless you, at the same rate as the average rate of this reaction, because the coefficient's 1, basically, in this case. Yeah. Question on that one there. Now, here we did it more of a kind of kinetics with the stoichiometry together. So let me just show you that if you wanted to do it more as a stoichiometry problem first, and then kind of incorporate the kinetics part of it, you could. So I see I'll maybe do it underneath here. So for example, if I was going to take more of just a stoichiometry approach up front, I'm going to pick up right here with my moles of NOBR, right? So that'd be kind of like a normal stoichiometry problem, right? Convert your grams to moles. You then could do the mole-to-mole relationship, right, between these two guys, which is a 1 mole of Br2 gives us 2 moles of NOBR, right? Or opposite, if I would have said it, wrote it right. So we'll go here. We'll take our 2.1836 moles of NOBR. We're just going to do a stoichiometry problem here. And again, 2 moles of NOBR gives us 1 mole of our Br2. So we're just going to relate it back over to our Br2 right up front. And that would give us 2.1836 divided by 2 will give us 1.0918 moles of Br2. At this point, we could divide it by the volume to convert it into molarity. So we'll divide that by 0.2, and that will give us a concentration of Br2 of 5.49459 molar Br2. Now that we have really the concentration of Br2, we can now kind of roll into the kinetics part of it. And that would be, if we look at our rate expression, the change in the concentration of Br2 over the change in time, we would take this up into here, and we would have 5.459 divided by our 300 seconds, which is our time. And lo and behold here, 0.0182 molar seconds. Yeah. So you can take a more stoichiometry part first if you want, and then kind of convert it into the kinetics aspect of it, and you'll get the same thing. The reason we do 1/2 is, what do I see right here? 1/2, right? So that's why we take 1 over the coefficient. So it kind of combos the stoichiometry part when you take 1 over the coefficient and puts it together with the kinetics part. But if it's easier for you, or if you want to kind of do it that way, in a lot of cases, you can kind of do the stoichiometry part and then kind of incorporate the kinetics part of it at the end. I would just say you got to be careful at the end there that you kind of incorporate all the kinetics part. You don't forget something. So sometimes doing the rate expression kind of puts everything together so you don't miss any component of it as you do it. Any questions on that there? All right, questions on rate expressions here. Yeah. So let's talk a little bit here about some factors that affect the rate of the reaction. The nature of the reactants, that means that what kind of reactant molecules and what physical conditions there are. Small molecules tend to react faster than larger molecules. Gases definitely tend to react faster than liquids because gases have a lot of energy. They're flying around, going to probably come in contact with people a lot faster. Liquids also have a little bit more energy, right, than say solids. So they're kind of floating around in the solution, a lot of the ions, for example. Solids are kind of just hanging out, hoping somebody does something to help them out. But solids also can be more reactive depending on the type of solid. A powdered solid is usually more reactive than a block solid. Again, it just has more surface area for everything to sort of come in contact with things. Certain types of chemicals are more reactive than others, like in single replacement reactions, right? That activity series, certain metals are more reactive than others, right? And that's why they can kind of replace them. And that has a lot to do with electrons being transferred and things of that nature. Ions are definitely react faster than molecules, because just in case you're not sure, ions are only found typically floating around in solution. Yeah. So they're floating around in the solution, which means they are good to go to start to react, right? They're not looking to do anything. They just got to come in contact with the right thing and the reaction can take place. Temperature is a really big effect on the rate of the reaction. Typically speaking, increasing the temperature will increase the rate of the reaction. The opposite would be true if you threw everybody on ice. Typically, the reaction would be a little bit slower. And that really has a lot to do with energy, obviously, right? So if you increase the temperature, you're adding a lot more energy, as you might remember, right? As things go from, say, reactants to products, there's this hill, right, that things have to climb. That hill is called the activation energy, right? Or E of A. So obviously, when you increase the temperature, you're going to find yourself with a greater proportion of molecules that have enough energy to kind of get up and over that hill a little bit easier. And the opposite is true. When you kind of lower the temperature, you're going to have a much smaller sort of proportion of molecules that's going to be able to kind of get up and over that hill to the other side. We will see a specific equation later on, which is known as the Arrhenius equation, which deals with rate constant and temperature as they change it. In general, a lot of times, if you just increase the reaction about 10 degrees Celsius, that's enough for a lot of reactions to sort of double the rate of it. Catalyst, which we'll also talk a little bit about as we go through some of these chapters, is another way that we can typically speed up a chemical reaction. And I would say in most cases, when people talk about a catalyst, again, they usually refer to it in the sense of speeding up a reaction. But as I mentioned, I think maybe the other day as well, there are negative catalysts, which are used to sort of slow down reactions that you might not want to sort of happen. Catalysts can be homogeneous, like a homogeneous mixture, right? Which means everything's the same throughout. And what a homogeneous catalyst means is the catalyst and like the reactants are in the same phase. You know, maybe they're all aqueous or something like that. Heterogeneous is just like a heterogeneous mixture. You see different phases, and the same thing here. A heterogeneous catalyst means that the catalyst and the reactants are in different phases. So a lot of times catalysts are again found written on the arrow. Sometimes catalysts are metals, right? And ultimately what a catalyst does is it finds an alternative pathway for that reaction to sort of take place, kind of a more efficient pathway for that reaction to take place. And ultimately how it speeds up the chemical reaction is it will lower that activation energy. So instead of the big hill it's got to climb in a catalyzed reaction, they just has to climb that sort of smaller hill by doing so. And that can be something as simple as it's a metal where if you have gases flying around, maybe they're attracted to the metal, so everybody gets into kind of the same location, and that's going to allow them to start reacting a lot faster than if that metal wasn't there and they're flying around trying to find each other. You know, kind of brings everybody into kind of the same location. A reminder as well that a catalyst is not a reactant. It is not a product, and it does not get used up in the reaction. Again, it is there really just to sort of facilitate that reaction occurring a lot faster. Now, in terms of concentrations, generally, the larger the concentration of reactant molecules, the faster the reaction will happen. And that's just, frankly, there's going to be more people bumping into each other, right? So if you have a very high concentration, you will have that happening. When we talk about molarity, which is moles of solute, right, per liter of solution. A solution, right, is both a solute and the solvent, right? And that's what makes up an aqueous solution. Out of the solute and the solvent, which thing is really reacting? The solute is really the thing reacting, right? So if you have like a sodium chloride solution, it's the sodium chloride in there that would be actually reacting and stuff like that. That is why when you have a larger concentration, that means you would have more mole, right, of your solute that's floating around in that solution. And again, a greater opportunity for those things to start reacting and stuff like that. Concentration of gases also depends on the partial pressures. Typically, higher pressures means you have a higher concentration of gas. Also, as you remember from Chem 50, if you have a high pressure, what happens with the volume? It does. That's a little Boyle's law action, right? So it decreases, which means if you have a really high pressure, your gas molecules are now in a very small location, right? Which means pretty good chance they're going to come in contact with each other a lot quicker, right? And it's going to cause the rate of that reaction to occur, as opposed to if you lower the pressure, you typically will have a larger volume, which means now everybody's got a little bit longer of a journey to try to find each other in that bigger volume. And that will probably slow down your reaction. And as I mentioned earlier, there, our concentration of our solutions is really what the solute is really what's going to be reacting. Obviously, the lower concentration as well, the opposite effect would happen. In a smaller concentration, you would have less moles, right, of your solute, a lot more solvent molecules moving around. So going to take longer for those reactions to occur. That's why sometimes when you do certain types of reactions, you should be careful about how much reagents you add, right? Every time you add a reagent, right, as we talked about, you're essentially doing a dilution because they're probably made out of water as a base. So you're diluting it. And sometimes you can dilute a solution so much that the actual moles of that solute that's in there is way too small to react because there's just way too much water, for example, and stuff like that. We don't do those type of experiments too much anymore. But there's a whole line of experiments known as qualitative analysis where you just add reagents. Sometimes people over add reagents and they're surprised when they get to the end test, which in those type of experiments could be like 7 steps down the road, and it doesn't work because they put too much reagents in there and stuff like that. Any questions on that? I feel like this is a big new topic here with the slide. All right, I'm going to lay it up here, I think. Any questions on